Welcome to the Cosmic Pie Podcast, Episode 17, Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We're broadcasting live here from the campus of the University of North Dakota here in Grand Forks, where we're melting. If I was a candle,
melting.
Robert...
What happened to North Dakota
I'd be a
spring?
puddle of
Jeez.
wax. It's that hot around here. The other day, we were like 99 Fahrenheit. It was like a 37 Celsius. And even today, it's in the upper 90s.
Right.
It's been like, this is like 3 days in a row or something?
4 days in a row.
Yeah.
The wind is ferocious, so that's welcome to the northern plains, but
Yeah.
the temperatures, these are, for us, late July, early August temperatures. So.
Yeah, for sure. Everything's drying out. The lawns are drying already before it had a chance to really get going for the spring growing season.
Yep.
And you name it. And, of course, the temperature is going to do what by the end of the week?
It's going to be more seasonal, and our highs are going to be in the 60s and upper 50s, so...
Hopefully it's warm enough I can still wear shorts and T-shirt after work and sandals. I hope it doesn't break out the long pants and the mittens and the scarf.
I don't think it's going to get that cool.
It is North Dakota.
It is North Dakota.
Global warming, right?
Yeah.
It'll never get that cold again, will it?
That's it.
Anyways, we do have a live chat feature that's running, so if you want to send us any comments or questions or anything like that, please feel free to use that option.
Indeed.
Also, disclaimer, Robert?
Disclaimer, we disclaim everything. I mean, that's not quite what he meant. The opinions and everything, thoughts expressed herein are those of myself and Wayne, not the Department of Physics and Astrophysics, the College of Arts and Sciences, or the University of North Dakota. So blame us.
There you go. So our first news item for today, it's an update of something that happened Friday night our time, so early Saturday morning. And this was the return of Cosmos 482. Now on this slide you can't see much, but if you look very carefully, sort of the center, top center, you'll see a sort of a little line there that says Cosmos 482. It's labeled. So this was an image that someone had taken from Italy of the last pass across that part of the country before it re-entered somewhere over the Indian Ocean. You know, they don't know for sure where it landed.
Oh, really?
Because nobody really saw it coming down like a fireball, which is amazing because you'd think that somebody would have saw it. Even if you're on a container ship in the middle Indian Ocean, that you might have seen this.
Huh.
But if it's daylight, then it's hard to see, I guess, but still should have made a nice trail across the sky, even in the broad daylight.
I would have thought so too. But, then again, it fell towards the north. So you're talking about that 52-degree inclination. It must have come in at a fairly high angle because it's in the northern sky, because I see Polaris on there and Capella.
Yeah, and actually it was tracing heading south, essentially.
Okay.
South would be southeast.
Okay.
I was kind of keeping track of it. They had live tracking of the orbit.
Right.
And you could see it going across Europe at the time, across Italy, across the Mediterranean, Saudi Arabia, down over into the Indian Ocean eventually, and crossing that way, sort of an angle.
Okay.
But the live trackers, they were on like a couple hours after it re-entered because nobody knew if it was there or not. So this is where it would have been if it would. And you could see it like tracking over different places of the world. It's like, hopefully it don't land there. But yeah, it was like afterwards they reported, no, it came down at about 1:24 a.m. in the morning, our time, on Saturday morning. So
okay, and this would have been the view from Rome.
Yes, exactly.
I just noticed that.
So this is so the next pass, no one saw anything because it was already down.
Right.
You kind of look. That's how you. I guess there's no. This was kind of weird. You'd think like NORAD.
Or somebody would have been tracking.
Or somebody's like live tracking it. That's a large object. It's not like it's like half the size of a golf ball or something, right? This is huge.
Right.
Type of object. And they would have that like live, like feeding it out. It's a good PR thing, right? Here's a live tracker of this object. So no guessing.
Yeah.
And then you could tell, right away, what is the altitude, what is the position. Not just projected forward in time based on its orbit when you don't have any real-time data to support whether the object's down or not.
Right.
That was the thing that I found disappointing.
Yes.
So it'd be nice if they could track this in real time. And the internet, you can broadcast that live. It's so easy, right?
I mean, I'm going to be a little silly here, but they can track Santa Claus every year. Why can't they track this?
Well, you think people would be interested because if it landed on your head,
If you landed on your head, get out. If you're in this area, get under cover.
So I just felt that was a little weird why no one had bothered to do that, but maybe the
Right.
next time they will. I don't know.
Hopefully there's not a next time. Hopefully we're getting better about control landing these things.
There's definitely going to be a next time because remember, this was launched in the early 70s, and there are a lot of stuff that's up there still that was launched decades ago.
And that's a good point for people. Back then, there were no treaties that said you had to do controlled deorbits. Now there are. So modern stuff splashes in the Indian Ocean or the Pacific. Stuff from the 70s, early 80s is going to come down where it comes down.
And since, the Earth is covered, 74% by water?
Most likely it'll hit an ocean.
Yeah, that's what you're hoping for if you're liable for any damages that may happen or life, that's injuries or anything like that. So, so we don't have to worry about it. It's down. Unfortunately, it never made its way to Venus. But nice to have this thing where it should have been on the surface of Venus. Sending us back, photos of a different landing site than what we've gone to already.
Right.
But and the other thing is, how come the United States has never gone to Venus with a lander? You notice they never ever bothered doing. They sent the Pioneer Venus probes in orbit. They had probes that re-entered Venus's atmosphere and sampled the information all the way down. But they didn't actually go to the point like the Viking missions,
where they put a lander down.
Where they put a lander down and do for some photography and some maybe even some quick sampling of the soil before the ship died under the pressure and heat. I know it's a harsh environment.
Yeah, and my guess is until recently there's been no interest in it, and I think that's somewhat political. The Russians have already done that and been there. Why would we follow, behind them? And so I think there was some of that, but scientifically, people were starting to get curious, and I happen to know that at the Venus chamber at Glenn, not Glenn, the one there next to Cleveland.
That's Glenn.
That is Glenn.
Glenn Research Center.
Glenn Research Center. There were some friends of mine that were working on projects there that were aimed at building circuits and things that would survive Venus for longer than 30 minutes.
Now, I know we're going back, right? Da Vinci was, I think, the probe. There were two of them. One of them was delayed, I think, because of funding. You may as well call it was canceled. The other one, I think, that survived was Da Vinci.
Right.
So that's going back to sample, I think, part of even the atmosphere and stuff like that. But there's no, real good probe like the Viking mission or even a rover, which would be even cooler.
Yeah.
And Venus is the size of the Earth. So imagine if you just land at two random spots on Earth. Does that really tell you the full story about the geology of Earth and everything else, what it's like? Obviously, it doesn't.
And the answer is no.
Yeah. So you really need to go back and look at this. But hopefully in the future that will happen.
Hopefully, yeah.
So we'll see how that plays out. Now, speaking about planets, we have another planet finder that's being constructed, that's in the works right now. And this is a mission from the European Space Agency known as PLATO.
PLATO.
That stands for, as you can see there on the slide, Planetary Transits and Oscillation of Stars. It's like just come up with some word like, I don't know, like Euclid or, anyone else like Archimedes or, this guy, Aristotle. And then figure out the words, what each of those letters represent.
I remember at a Sagan exoplanet conference that I went to, we were presented as a project to make a cartoon mission or system to measure exoplanet atmospheres to get spectra of them. And I remember a big part of our discussion is what was our acronym going to be? See, there was a point to the story.
Right.
What was our acronym was important enough that it got discussion for a while. So these acronyms, people do make a lot of them.
We have to come up with something like for cosmic pi.
Yeah.
The cosmic orbital sensing
instrument
microscopic instrument for challenging planetary interior. There's behind.
Yeah. Something like that.
Something like that. So the PLATO mission, as you can see there, is going to use like transients. So blocking the light.
So, and oscillations. So it's suggesting to me they're planning on looking at variable stars in general, too.
Yeah. And the very cool thing about this mission is that it'll have cameras. So you can see there, they just finished installing 24 or 26 cameras. That's kind of why this was on the news lately. It's on the slide you see on the right-hand side. The field of view of this telescope, this is amazing. 2,250 square degrees. Now, for perspective, for 1 square degree, that fits a little more than 4 moons.
Right.
In fact, this 2,250 square degrees represents about 5% of the total sky.
Right. And
in one image, you can image 5% of the sky. So this is the
they're gonna find a lot of planets.
This is the selling point. All the ones that have been launched to this date, TESS, Kepler, and others are all narrow field of view compared to this one. This one's going to be able to sample a huge swath of the sky. And there's another interesting twist to this mission. Look at the target stars. You see that in the bottom left?
I was noticing that. They're going a lot dimmer.
No, the opposite.
Opposite? I thought Kepler was brighter than that.
No, TESS and Kepler are actually they were going on the faint end.
Okay.
And they ran into, here's my understanding. It may or may not be true. But my understanding was for telescopes to do follow-up to these objects that were detected by prior missions like Kepler and TESS, that's up there now, the magnitudes of the exoplanets, the dips, if I should say, that the exoplanets caused.
Like 0.01 millimags.
Right,
yeah.
and you're talking about very faint stars. They couldn't get a good signal-to-noise measurement of a lot of those candidates.
I don't doubt it. I really don't.
The host star itself is just too faint.
Okay.
So ESA decided to select brighter stars. So they're selecting between 4 and 11th magnitude in the visual, so they'll be able to use ground-based telescopes to follow up all the possible detections of the planets.
That's right, because, in V magnitude, I found the limiting magnitude in suburban skies was about 14, 15.
Yeah.
So this is brighter than that. So...
Yes, that was the problem. You need that really high signal to noise to get a good measurement of the light curve and all the subtle features in the curve.
Right.
And so you're talking about observing fairly bright objects.
And you need to see those features because that's really what distinguishes it from being a variable star or occulting binary or any of the other things that can cause light dips.
And you can also get some information about the various properties of the candidate planets.
Right.
Get some more information about their albedos, their masses, their orbital characteristics.
And possibly even spectra from their atmospheres.
Yeah, the higher the signal to noise, the better that is.
Yeah.
So that's the logic behind this. So the spacecraft itself is due to be launched. It's not a firm date set. It's just the end of 2026.
Okay.
So they're obviously putting it together now.
So a year and a half.
But we're going to see a lot of cool stuff from this. If you can observe a huge area of the sky, it's amazing to think of the data you're going to get.
5% of the sky? Is it going to be like Kepler pointed at one section of the sky, or is it going to move around?
All sky survey, buddy. All sky survey.
That makes me happy.
It's going to be amazing because don't forget the LSST is coming online soon, the telescope.
Oh, right.
So that'll be able to do... it's going to be doing surveys too, so there's going to be a lot of follow-up potential for a lot of telescopes.
Yeah.
In fact, this may be a selling point now. At 4th magnitude, you can easily measure these dips probably with a 16-inch telescope in your backyard.
Absolutely.
And be able to follow up a lot of these candidates.
I've detected in that magnitude range, I've detected several exoplanet transits with a 14-inch telescope. In that magnitude range.
That may be what's going on here is they decided, there's a lot of large amateur telescopes that people have nowadays.
And they can do follow-up observations.
Just as well as, professional telescopes. There's not a lot of them compared to the fact that once the LSST is up and running, right, the Vera Rubin telescope is doing its thing, there's a huge number of telescopes in the south are going to be dedicated probably to following up a lot of those objects.
Right.
So who's going to follow up
These
things?
PLATO objects.
Yeah, and so any amateur can be able to
I'll
do
raise
that.
my hand. I volunteer as tribute.
Yeah, that's going to be really, really interesting.
Oh, yeah.
Now, talking about another mission, it's been proposed but not funded, so who knows, right? Now, we have a stores around here called what? Hugo.
Hugo's, yeah.
So this is LUGO. There we go with the acronym again. Lunar Geology Orbiter. LUGO.
So
Its primary purpose will be to investigate what they call irregular Mare patches. In fact, example of what you see there in that mosaic, which is mainly images taken by the Lunar Reconnaissance Orbiter, are collapsed lava tubes. Now, if you look at them, it's like looking down in a well on the moon, right?
Right.
And in fact, people suggested that, number one, I wonder what the bottom is like. Can you actually stand there without collapsing down, a couple hundred feet or something? Is there any tensile strength to the bottom of these things? So they need to be investigated, but they act as sort of a natural shelter.
Mm-hmm.
So you can imagine that a solar flare goes off.
You scramble and get down
and get
into
inside
one
of
these
these things, and it's possible that you can help get away from that radiation
Right.
until the event goes away, right?
Right.
Then you're done. So these will definitely be investigated in the future. Robotic at first, because who wants to be the first person to
Woohoo!
tie a rope to me? Don't let go. I'll go down, but you got to make sure you have that rope.
Right.
But yeah, all these type of irregular type of geological features, that's the primary purpose of this mission. So that'll be interesting. It's like, a fine type of structure that you want to investigate eventually anyways. You sort of do the coarse grain type of analysis by taking, large scale images of the surface of the body and so on. Then you start going back and investigating all the little tiny things that you see that could be interesting. Right. And this is some of it.
I mean, I got to admit, these pictures, these images reminded me a lot of some of the messenger images that were sent back of craters. So I thought there was some playing around with the relief. Like
Messengers, you thought about Mercury then?
Mercury.
Yeah. I think somebody's even been on Mars.
Okay.
Some of these type, but don't quote me on that. Right? These type of features. But yeah, these are really cool when you think about it. But lava tubes, so you know what that ties into?
Volcanism. The moon was once volcanically active.
Yeah, I remember that was the great controversy, especially prior to the Apollo project, is all the craters were they created mainly by volcanoes or impacts.
Impacts, right.
And it turns out they're impact features, the vast majority, but there is evidence of volcanism on the moon.
Mm-hmm. Including the mare themselves, those vast basins of basalt. That's
and lava flowed over.
Lava flows.
And that's why the far side of the moon, the back side of the moon looks different than it does on the side that faces the Earth, because it doesn't have those large lava fields like we have on our side, which is interesting in its own right. Why is that?
Well, I've got my ideas from the papers I've read, and some of them forward the idea that it's the tidal effects of the moon having at the time been much closer to Earth.
And not tidally locked like it is now.
And not tidally locked like it is
So the
now.
same side of the moon that we see today, it would not be like that go back several billion years.
Right.
We'd see all of the moon all around it.
Mm-hmm. And yes, folks, the moon is still rotating, but it rotates at the same speed as it orbits Earth. So.
Yeah, so that's about once a month.
So its day is the same length as its year, essentially.
I mean, the only sampling that's been done on the far side of the moon is recently by the Chinese.
Mm-hmm.
So we definitely have a lot of exploration to do on the backside to sample the chemical composition to see if it's the same as the near side, and if it isn't, what are those differences and why are there differences?
Absolutely.
That's
what we're all interested in is if there are differences, why are they there?
You know what would be fun, Robert?
What's that?
If they discovered methane on the moon.
That would be fun.
Now, where does methane come from?
Volcanism or biologic.
What? Hold it. Back up, sir. Back up.
Okay.
Volcanism, and what was the next thing?
Biologic.
Biology.
Yep.
Critters. Lunar creatures.
Yeah, I would find that to be quite a phenomenal find if that came about. So.
Well, maybe for the moon, but maybe not the case for Mars.
Maybe not for Mars.
In fact, methane has been detected on Mars.
Right.
I guess the greatest question is this, if you like, geologic,
Biogenetic.
or is
Biogenic.
it from life? Yeah.
Yeah.
So this is a recent paper that came out which caught my interest, and what they suggest is that some of these detections that the Curiosity rover is making on the surface of Mars, where they detect the presence of methane, is actually due to the instrument on the rover itself.
Right.
And if you actually read the paper, it's interesting in the fact that they think that the detector has been compromised. These things are sealed under their own pressure. And the authors suggest that that's not the case with what's here on the rover itself.
Okay.
That the seal was damaged somehow or compromised somehow, and that they actually can detect pressure changes over the course of day and night that would reflect the fact that the seals are not valid.
Right.
And they offer a test, taking measurements of methane and then waiting, another location, another time to test it again, time of the day, to compensate for the pressure changes. So it's
that's a good test.
yeah. So that's what they're proposing. Whether NASA does that or not, who knows? But it's these fleeting things where now you detect it, now you don't.
Right.
So is methane really there or not? In fact, some orbital missions, even the one from the Europeans, the Mars Express mission, I think it was called, they detected methane and then they didn't detect it and then they detect methane. It's like almost like this elusive ghost running around on the surface because methane's so important, as you suggested. It could be linked to, bacteria-like creatures on the surface, right?
The problem is until you get out to the deep freeze portion of the solar system, Jupiter and further out, the outer planets, there's enough solar radiation to dissociate methane into carbon and hydrogen and so forth. So methane in the inner solar system is very short-lived. So if you detect it, it means something is replenishing it. And the question then becomes what's putting it back up? So any detection of methane is interesting.
Yeah, so it'd be interesting if NASA or whoever's in charge follows this paper and actually tests to see if there is something to do with the instrument. So it's an internal thing.
If it's an internal thing or if it's really
detecting
of
methane variations on the planet. So that'd be kind of cool. This is kind of stuff, that humans would be good at.
Right.
Because you can troubleshoot on the spot and actually be able to change things up in such a way.
Or enact repairs if it's reparable.
All that kind of stuff, be able to tell. But you can do it by robots. It just takes more time. Mm-hmm. And, of course, the cost of sending people there is so astronomical, should we say?
Yes,
that
maybe.
It's well worth it to wait a while, even if it takes several months to figure it out with a rover rather than, a couple days with a human being on the surface.
Right.
But it's funner to have a human there, obviously.
Obviously.
Imagine the viewership you would get if we landed on Mars.
It would probably be as big, if not bigger, than the moon landing. Yeah.
And look at how you would inspire young people, especially, to get involved in higher education, engineering, science, technology, all of that kind of stuff.
Yeah.
And you don't know the untold ramifications of that in the future in terms of development of different, sort of in economic type of stuff, right? So the return on the dollars
is phenomenal. It's huge.
Yeah. So why don't we invest in that rather than building bombs and killing people or something, That's the question for the day and for the century.
Yep. And for human history, so.
Yeah. Anyways, so the next kind of thing that caught our eyes is event called a tidal disruption event. So these have happened a lot, and people there's been more study in this in the last couple decades, I've noticed, than prior. And a lot of it is not always, but it's usually associated with a compact object like a black hole or a neutron star or something like that. And what you'll get is material or even a star that passes too close, gets snatched, if you like, by the gravitational influence of these compact objects. And the star can be tidally disrupted, like near a black hole or something like that. That material, it gets heated up through the gravitational tidal effects, and ultimately most of it will probably fall across the event horizon and disappear, if you like, from the universe. But the light itself is given off by that material just outside of the event horizon. So you get this like a flaring type of event that can occur. And that event can occur in multiple wavelengths, X-rays, even gamma rays, optical light, and so on. And people keep track of these objects because if you didn't know like a compact object existed until you've seen one of these flaring up events, that's like a red flag being raised saying, hey, I'm right here, come look at me.
Because there's no other way you're going to see it.
It's hard any other way to do it. And then all of a sudden you'll train telescopes at different wavelengths to look to see if you can puzzle out what caused this type of event.
Right.
And it's mostly, like I said, associated with these compact objects. In fact, this slide kind of shows that. In this case, it's using a black hole, which is look at the top panel on the far left, and you see a star that's coming too close to the black hole, gets captured by the black hole, gets shredded. The material then falls into the black hole, but it gets heated up and emits this burst of light, which is what you're seeing as this tidal disruption event itself. So one of these events occurred recently. This is in a galaxy about 708 million light years away, so it's not in our backyard at all. And you see the image of the galaxy taken on the far left there, and you notice that the arrow that I put there pointing to a bright spot. If that points to the supermassive black hole that's in this galaxy, that usually should be at the center. And it's not in the center, it's offset. In fact, it's offset by about 2,600 light years. So for this particular galaxy, there are two supermassive black holes, one at the center of the object, the geometric center, and one that's illustrated by this bright spot. And that bright spot is one of these tidal disruption events. Okay.
Well, that suggests that it falls in line with our hypotheses about galaxy formation, because that would say this galaxy is as a result of mergers of one or more, and the supermassive black holes haven't merged yet.
Yeah, that could exactly be the case. We just don't know. You have to look for signs of mergers. I don't see anything obvious in the image of this galaxy, but it doesn't mean it's not there if you study it in more detail.
And it would mean that the galaxy merges into a singular entity long before the supermassives merge.
Now, if you look at the different masses, the one that created that bright little spot where the arrow's pointing to, it's estimated the mass of that supermassive black hole is 1 million times the mass of our sun. Now, just for sort of sense of reference here, the supermassive black hole that's at the center of our Milky Way is a little over 4 million times the mass of our sun. So this is only 25% the mass of the one in the center of our galaxy. Okay. The actual supermassive black hole that's in the center of this galaxy is estimated to be about 100 million solar masses. So
it's swallowed up a satellite galaxy or something.
It could be a smaller galaxy, and that would explain, could be, in other words, if the situation or the process where a massive galaxy consumes a much lower mass galaxy is known as galactic cannibalism.
Mm-hmm.
So it could be that this galaxy you're seeing here cannibalized a much smaller dwarf or satellite galaxy, as we call them, a low mass galaxy. And that's the resultant black hole that was at the center of that low mass galaxy.
Right.
The only other way to explain it is it have to form sort of in situ, right, in place of where you see it. And it's always a big mystery, of course, how do you form these supermassive black holes? Some of them are billions and billions times the mass of our own sun. These are on the scale of millions, an order of magnitude smaller, but still, how do you form them?
That's the question now, isn't it?
And James Webb's kind of turning the vice on this.
Okay.
Because we thought it takes you a certain amount of time to form these supermassive black holes early on, but we're finding them at earlier times with the JWST.
So which means they form quicker.
A lot quicker. The time scale that you have to work with is a lot shorter than what we thought we had. So it's becoming uncomfortable. That's where you pull the neck of your shirt out a little bit and give it a couple tugs, right?
Right.
When it comes to forming galaxies. It doesn't say anything about the universe itself. The universe couldn't care less.
Right. It just says we don't know how galaxies form.
Yeah, just the detailed process of galaxy formation, and in particular, the time scales. How much time do you need to actually form a galaxy? Yeah. We thought it was billions of years, but can that reduce down to hundreds of millions of years? In fact,
it looks like it can.
Well, the most distant galaxy is nearly, it's so far away that we're seeing it as it was about 280 million years after the Big Bang. So it formed in less than 300 million years.
Right.
Talking about turning that vice and squeezing things, you see?
Yeah.
We're really down to that point of no return. So that's an interesting thing to follow. But so where did that supermassive black hole come from? And coming from the merger of a smaller galaxy is probably like the best explanation for that. We see the images on the right there, taken both with the Hubble Space Telescope, Chandra, so you get X-ray observation. That's in the top far right column, the top panel, and then the bottom one is VLA. That's the Very Large Array in Socorro, New Mexico. So it's radio telescope, radio observations. And the object that you see in the upper left of the panels are that little dot that you see there, right? So you can see they're zoomed in. So both of them are for the radio on the VLA. Notice there's more coming from the smaller one than it is from the other one. Because it's a tidal disruption event, so clearly there's material there that's emitting light, including at radio wavelengths at 10 gigahertz, which is the frequency.
Whereas the central one is not.
Yeah, the central one's not
feeding at the moment.
Yeah, so it's not an active galaxy, right? It doesn't have that large accretion disk. So so that's the difference there. So, anyways, this is kind of interesting, and all of that is described, in a paper that's been submitted for publication. So people will study these things. And the other thing is, are there more out there?
Yeah, because that would be interesting.
This type of cannibalism that occurs is fairly common, especially in dense regions.
Mm-hmm.
So one should look in places like galaxy clusters to see if you can find the incidence of these doubled nuclei.
Right.
These maybe find some more of these tidal disruption events. Get lucky. Keep watching these galaxies in galaxy clusters to see if all of a sudden there's one there, in some galaxy.
Well, it's always neat when you find a sample size of one, but you really can't say a whole lot until you get sample sizes that are larger.
Yeah, you just got to think of where would these things occur more frequently, and that would be where there's a lot more
galaxies
around that can be cannibalized, eaten up, and that's in these dense environments like clusters themselves.
Cool.
So we'll see how that plays out. Okay, so the other thing I want to talk about, and then Robert, you have some things that you want to talk about.
Yep.
This one here is a paper that was just published recently, and the title of the paper is Dark Matter Axion Search with HAYSTAC Phase 2. And you see the title, No Needle in the Haystack. And the reason I put that there is because HAYSTAC is an instrument. In fact, if you go to the next slide briefly, you can actually see the instrument itself. So it's an experiment to detect a particle, a hypothetical particle. We have never detected these particles before, known as axions. So axions were first proposed way back in the late 1970s. Frank Wilczek and Steven Weinberg independently proposed this particle. And the particle was proposed to explain the non-observation of CP violation and quantum chromodynamics, QCD. Quantum chromodynamics.
So what's a CP violation?
Okay, so CP violation is if you take a particle and switch it out with its antiparticle, that means charge conjugation, it's been switched, and you replace it by the other-handedness instead of left-handedness, right-handedness. You think of the spin of the particle. That's parity. So if you change both the charge conjugation and parity, there should be a symmetry. Like you wouldn't notice the difference. Okay.
Except you do notice the difference.
Except you do notice the difference. Except that you don't see that in quantum chromodynamics. You see it in other stuff, but not in quantum chromodynamics. And QCD, by the way, is just a fancy term that explains the interaction of hadrons. So you heard of the Large Hadron Collider, these kind of things. So you're talking about things like, protons and neutrons. Particles made of quarks, in other words.
Right.
Okay. So the quantum chromodynamics explains their interactions. The other one that goes with this is QED, quantum electrodynamics, and that explains the interactions essentially of electrons and photons.
Okay.
That type of interactions. So anyways, there's been no CP violation that has ever been observed in quantum chromodynamics, the interaction of hadrons. And that goes against the fundamental theory that we have, the baseline standard model.
There should be CP violations.
There should be CP violations. And because
we
we don't see any, then it was proposed in late 70s that there should be this axion particle that would exist. And the interaction with the axion particle makes it so that there is no CP violation, which would explain the observations. The problem is we haven't seen the axion particle.
Okay.
We look, we just haven't seen it yet. The other thing that's really cool, which is why we're interested as astronomers about this, is that these particles would have a little tiny bit of mass, tiny bit. Like you're talking about sort of micro electron volts, and right, a little tiny bit. But there would be all kinds of them everywhere. And in fact, they would, it turns out, because they're very weakly interacting with anything else, that they would be a perfect candidate for
dark matter.
Dark matter, to explain things like the flat rotation curve of the Milky Way and other galaxies and so on and so forth.
Now, I want to ask, I don't know if you know the answer or not, but why wouldn't they at this point start looking for that it's a problem with QCD theory?
There's a lot of experiments that have been done in decades since QCD came out. These results analytically are very tough. In fact, you're pretty limited on what you can actually calculate, pen and pencil. So a lot of the stuff is calculated using simulations on a computer, and even then, it's really, really tough. And they do that, and as far as we know, QCD is a good representation. It's a good model. It'll give you at least approximate what goes on in these interactions of these hadrons, like you would get in large hadron colliders smashing protons together, and these scattering experiments that you do. So they're very difficult. In fact, you have to use a lattice to do the calculation.
Oh, Jesus.
Because of divergences that can occur. It's really, really technical type of stuff.
Yeah.
Okay, so QCD seems, in its present form, seems to work very well. And of course, physicists are always begging for something that doesn't work, because that means there's something wrong, not quite right with the model, and that may lead you into a better understanding of the interaction of fundamental particles and tell you something new. So QCD plus or something, right? So we're always looking for that. So the axions should exist because we don't observe this the CP violation. Yeah. So whether or not they're there or not, that's the thing, right?
So if we don't find these axions, it suggests then that there's some tweak that needs to be done to QCD.
Probably, you know, or you got to have some other way of figuring out why the CP violation is not observed.
Not observed. Right.
But it's interesting. These particles, these axion particles, are so weakly interacting. You can see their description that I put down there. How do you find them to begin with? They're so elusive. How do you find that thing? Well, that's the problem.
Right.
So you try to think of ways that these things would be better able to be seen compared to other ways where they essentially hide. It's like somebody writing you a paragraph in invisible ink. And if you don't know anything about how to make that invisible ink visible, what they wrote, what do? Right? You could search all kinds of ways of trying to do that. And so the way that they're using here in this instrument, the HAYSTAC, is something that others use. It's using the haloscope. By the way, HAYSTAC, here's one of those acronyms.
Yeah.
It stands for Haloscope at Yale Sensitive to Axion Cold Dark Matter, even though there's more people than just Yale that are involved, more institutions. Right? And I'll show you that in a second. Here we go back to the previous slide in a moment. But what they're doing is they're using a very strong magnetic field to coax the axion field. So every particle has a field. This is quantum field theory.
Right.
So, for example, the electron has associated with it the electron field. A proton's made up of up and down quarks. So if you go to the basic fundamental limit of what's going on inside of a proton, the up quark would have its field and the down quark would have its field. So you have all these fundamental fields associated with all these particles. So the axion would have a field. And you can think of the axion particle, and I'm putting air quotes around it that you can't see me doing here. That's like a excitation in the axion field.
Okay.
The undulations in the field at a relatively localized region. That's what we mean by a particle. So particle's not like a ball bearing.
Right.
That was the old way of thinking about stuff that's long since been shown not to be correct. Even though we still go to that immediately because it's just easier for our mind to wrap around where we know what a ball bearing is. Everybody's got experience with little, discrete little particles like that, right?
Right.
So you can coax one of these axions, these excitation in the axion field, to rear its head. If you have it in this strong magnetic field because any oscillations in that field can be converted into an oscillating electric field.
Okay.
They get coupled together.
They get coupled, right?
And what you do is you have this experiment that's operating inside what they call a resonance cavity. And so that allows you to tune.
So that you can pick up and amplify the signal.
Yes, exactly, because the signal will be extremely weak, so you need to amplify it. And in this amplification process, essentially microwave photons can be created. And it's those microwave photons that get detected.
Right. Not the field itself,
Yeah.
but the microwaves that are produced by the interactions of the field.
Yeah, it's like if I kicked you in your left foot and you automatically kicked out your right foot, which then hit a domino, and we had a big line of dominoes going all over the place. And then the last domino, I don't know, hits some other device that drops an egg on the floor and the egg splats. All you see is the egg splatting. You don't see any other interaction occurring. You'd wonder, how did that happen? And it's like this one thing preceded another thing, preceded another thing. And in concert, they work together like this machine, if you like, to cause the event that you observed. So cause and effect type of thing, you see. Anyway, so far there's been no detection. I want to go back to the previous slide. Sure. No detection then of the axion, unfortunately, but people are looking. You can see that the title page there of the paper itself, there are different people from different places at Yale, University of California at Berkeley, Johns Hopkins University as well, and University of Colorado at Boulder. So there are a lot of different institutions involved, not just Yale, which is part of the name, because that would be confusing.
It's probably because it's housed at Yale, I would imagine.
I'm not sure. That's good.
Okay.
Good question. But the experiment itself, you can get some results there looking at microelectron volts. So they have a range of what they would be sensitive to. And the paper is phase 2. And why it's phase 2 is because they utilize a technique that's also being utilized, as far as I understand, by LUGO for detection of gravitational waves, known as quantum squeezing.
Yes.
Okay?
I've heard the term.
And that's a way of reducing the quantum noise. So there's this inherent quantum noise that you will be exposed to. In fact, it can dominate the signal when you're trying to detect something so subtle like these axions. So it's like thermal noise when you're doing, less sensitive type of experiments, right?
Right.
You can go down to what is the lowest temperature you can attain in your laboratory. And temperature just means the average motion of things, the average kinetic energy. So what you would do is if you imagine you had an ensemble or collection of atoms, and some of those atoms are going to be moving faster than average, some of them slower than average. So you try to peel off all of the fast-moving atoms so that overall the average motion decreases, which means the temperature goes down.
Right.
So you keep doing that, and you go like, what's the fundamental limit? You get to the point where just the background sort of leftover particles that manage to interact with each other have this thermal agitation, and you can't go any lower than that. And if you go lower than that, then you're in the quantum realm, essentially, and the same kind of thing is happening here.
Right.
So it's a technique, which is really technical, so we're not going to go into it, where you can reduce that background noise even further to hopefully be able to see the very subtle oscillations of the electric field from the excitation of the axion field. That's the idea. So anyways, the important thing is, of course, is no detection so far. In fact, I'm starting to get worried. I'm old enough to be around many decades now of this dark matter experiments that I'm starting to really wonder.
They're not finding
Really,
anything.
let's be honest, right? Let's just pretend it's you and I, Robert. No one else is listening to this podcast.
Okay.
It makes you really worried that dark matter is not even there at all.
Right.
And then we have a lot of explaining to do in a sense of what causes the observations that things that we actually observe. What actually causes that if it's not dark matter?
I'm there with you. At the same time, I'm very excited about that because that's new physics. That's new stuff to find.
Yeah,
so I can't be mad about that.
Yeah, just finding the dark matter candidate is new and interesting.
Yeah, it would be interesting in its own right.
But if it's not there, and we tried, you look everywhere. Right? You look in the corners of a darkened room. You turn on the lights. You don't find this particle anywhere, or particles. Could be more than one, of course.
Right.
Then what the heck is causing all of this stuff that we see that looks like there's dark matter around?
Because I will go ahead and address that too. There's, people trying to modify Newtonian dynamics to explain galactic rotation curves without dark matter. But the problem is there's more observations that aren't explained by that adjustment to Newtonian dynamics. What do? You can explain this one thing, but you can't explain all the other things.
Yeah, classic examples of the bullet cluster.
The bullet cluster.
And so if you're interested in that, you can look that up on Google, what the bullet cluster is. But it's a set of observations in the X-rays and using gravitational lensing, so we can tell what is the total mass of these two clusters that kind of went through each other and is on the other side going away from each other now. And you can see that the hot gas is trapped at the center because that hot gas, which we observe by X-rays, that hot gas fills up a huge volume of space. So you can't push it through each other without interaction. So it's interacting, stopping each other, caught in the middle. Where the dark matter is spread out enough that and it's weakly interacting, it can pass through each other and continue on their merry way. So you see a spreading out of the density enhancements on either side, which is the dark matter, yet the normal sort of matter, the hot gas, is trapped in the middle as observed by X-ray emission. And modifying Newtonian dynamics, as far as I understand it, in its present form, is not able to fully explain it. In fact, some people who just scoff at MOD, which is the modified Newtonian dynamics, say that they actually need some amount of dark matter to explain the bullet cluster observations, but not as much as what you guys need to explain other stuff. Well, you either need it, it's either there or it's not there, right?
Right.
You can't say I only need 10% of it, so my idea is better. It doesn't work that way.
Right.
The idea is that it shouldn't be there at all. And what MOD works, by the way, is the fact that the gravitational force, as it relates to distance, changes. It's not as Newton has described it.
Right.
And since we're talking about things over galactic scales, that gravity does not operate with the same strength as what we thought. If you change that dependence of gravity on distance over large scales, then you can reproduce some of these observations that we observe that indicate that there is this dark matter. In other words, there wouldn't be any dark matter. It's just that gravity operates differently than what we thought.
But they can't explain lensing, mass lensing from general relativity. It can't explain this bullet cluster process.
Yeah, and so there's a lot of there's a lot of problems here. But where's the dark matter particle?
Right.
Is it primordial black holes? That's becoming more favorable. I noticed the last couple of years.
But where all the little ones popping off because they've evaporated.
Yeah, and there's all kinds of other things, right?
Yeah.
You just haven't observed any, so that can be a problem. So we're still looking. That's the summary of that, I guess. So
yeah.
Now, Robert, you had some stuff you wanted to show?
Yeah, basically it's revolving around this paper, this idea. It's not being produced very clearly here, but a main sequence star appears to have consumed its planet, a Jupiter-sized planet, and they had confirming observations with, as this paper shows, with JWST. And the reason they think, go ahead.
I was going to say, before you go on, maybe you can explain to people who don't know, what is a main sequence star?
Okay, main sequence star is your average everyday star. It's converting hydrogen into helium in its core through one of several different possible processes, depending on its mass. But it's not swelling up. It's not dying, in the process of dying yet. And it's not being formed. It's not accreting mass yet anymore, I should say.
So how would you compare that to our sun?
It's like our sun.
Okay.
Yeah. Our sun is right in the middle of its time on the main sequence.
Yeah. So that's the first stage of the lifetime of a star.
I like calling it the adulthood, because you've got the Herbig Haro era where it's just throwing tantrums left and right and brightening and dimming and brightening and dimming. And then you get a kind of a young adult where it's settling in, but it still flares. And then you get the main sequence.
So it's like a 30-year-old person who stops partying and settled down and got married.
Right.
And just thinking about having a job and trying to build up a nest egg for the rest of their professional career type of thing. That's stability.
Stability is the word to apply. Yes. Right. It's stable. It's doing what it's supposed to be doing.
Okay.
So anyway, a flaring event on this star was observed where it suddenly brightened. And it couldn't, as this next slide, so what they think happened is that this Jupiter-sized planet was slowly spiraling in due to tidal forces, tidal effects. And so pre-engulfment, you would have seen just the host star, but afterwards you would have seen a cool, dusty ring that was being slowly dissipating, and a remnant around the host star in its spectra. So they compared it to other types of flaring events. So an outburst or a classical nova or another type of outburst, or it was a dwarf star. And as you can see by all these, the blue, the green, the magenta, yellow, and red, they don't match up the black spectral distribution that this event produced. It's nowhere near similar to any of these things.
Okay, so the one you're talking about is the one sort of right on the left side by scaled, the word scaled.
Yes.
It's spectrum.
So it's color-wise, it's black.
ZTF, so that's like the Zwicky transient facility or
that's
something,
it.
Right, or factory, I forget.
SLRN 2020. I forget what the SLRN stands for, but basically this brightening event did not follow the pattern for any of the other types of nova or brightening events that we know.
I noticed that the spectrums that are at the top all have very strong H-alpha emission.
Right.
And you don't see that in this at all.
You don't see that at all.
So that's tell you a lack of hydrogen?
Lack of hydrogen. Lack of hydrogen. And there are other features like up towards the upper right part of that curve, you see that dip and then lots of little spikes. These are indicative of other elements, heavier elements.
So what's the scale at the bottom? The x-axis?
I just noticed when I was loading these slides that it was cut off. I think it's wavelength.
It's wavelength. It must be, is that microns?
Microns.
Okay, so dust itself. So if it's a ring of dust, that would glow brightly at infrared wavelengths.
Mm-hmm.
They're not quite there. We're only up to 1 micron. We really need to get to the far right of this plot. But you need infrared observations.
Or we need this, a spectral energy distribution.
Oh, here we go. There's microns on the bottom.
So we've mentioned spectral energy distributions before, and this is what we're looking at. And this top curve, black curve, is the spectral energy distribution 320 days after the flare, after the event happened. And then the lower gray one right below it is a 830. So much as we expect, if it was a planet being consumed, there was a lot of dust, because this is the profile for dust, because that's what those yellow dashed lines are the profiles for dust emission. So dust is being heated up and it's re-radiating the energy it's absorbed in infrared. So as you move into the infrared, given by the wavelength at the bottom, it's brightening.
Now you have a couple different dust curves there.
Yes.
So what separates them? Temperature or composition or both?
I think it's temperature.
So
I only had a very few minutes looking at this. So from past experience with SEDs and dust, because that fits with my planetary formation interest, it's probably different temperatures and profiles of dust.
Yeah, they both have a bump out at 10 microns. You notice that?
And that's
probably
typical.
PAHs, polycyclic aromatic hydrocarbon emission.
You got it.
Yeah, okay.
You got it. So that's the emission from a particular type of carbon molecule that absorbs readily infrared and light visible energy and re-emits it at about that wavelength.
You know what PAHs, where you can get that here on Earth easily?
Probably from petroleum.
Yeah, diesel exhaust.
Diesel, okay.
You suck back the tailpipe of a truck running diesel. Amongst the nastier things that you're going to swallow, part of that is the PAHs are in there. And they're out in space. It's amazing to think about. It is. So,
I mean, this is why panspermia is still hanging around as a theory, which panspermia says that life is basically scattered throughout the galaxy, are the ingredients necessary for it, and it gets seeded onto planets like Earth. And it hangs around because all these PAHs are out there, methane, ethane, amino acids, all of these ingredients are out there.
So you're seeing two light curves. Looks like one 320 days.
And one at 830 days.
830 days. So the Zwicky Transient Facility, so that's a camera on a telescope at Palomar Observatory. And they've been running for quite a while now, doing very large, wide area surveys, imaging of the sky, looking for things that just appear all of a sudden. And like,
Right. That's exactly what they're doing.
Hence the word transient, right? Looking for it, which is really interesting. It's a nice niche in astronomy, is looking for what is changing, and that captures your attention once again, as we said with those tidal disruption events.
Right.
So we're looking at dust, and it looks like they're saying that it has about 10 to the minus 6 solar masses of dust. With is that an optical depth, 1.2? Is that what that is?
That's it. That's what that is.
And they're showing you the arrow there, what the dust component and the spectral energy distribution would look like 830 days after the event itself.
Right.
And that's consistent with the observations, right?
That's consistent with the observations. So basically, you would have a dense dust cloud for a short, that gradually it would heat it up, giving off a lot of light, but as it dissipated and spread out after the event, you would expect it to cool and not radiate as much.
What a nice thing to observe with JWST, with the infrared.
Absolutely.
And you get the spectra with it as well.
And
you'd be able to find a lot, probably about the composition of the dust and everything.
Yep. And I was not able to find any spectra of that from JWST.
So the dust is from the Jupiter-sized planet?
Right.
And because that comes from 10 to the minus 6 solar masses of material that you want. So where's that dust coming from, the dust part? Because when you think of Jupiter, you don't think of dust. You think of more primordial material, right? Hydrogen, helium, methane, this kind of stuff, right?
Right.
So where does the dust coming from such a large Jupiter-sized planet?
Because Jupiter being the size it is, it does have a significant component of dust, of particulate matter that's in the atmosphere. Now, it's significantly less than the ammonia, the water, the methane, the helium, the hydrogen, but it is there. It's also potentially from a core.
Well, that's what I'm thinking, because we know Jupiter has, metallic hydrogen potentially.
Right.
So
whatever that means.
It's far away. Well, you think of the conduction of electrons, right? They're in the conduction band.
Right.
Everything's driven up there. But it's like a superconductor in that sense, right?
Right.
But think of I'm just wondering the survivability of dust grains. They're relatively fragile. Right? It doesn't take much to destroy the dust grains.
And that may be also why we've got a decline in the SED, a lowering of the energy being the flux coming from the dust. It could be it's dissociating.
But when we're talking about Jupiter-sized object, right?
Yeah.
Maybe we're not thinking it the right way.
It could be.
We're thinking in terms of size, but the actual composition is completely different from Jupiter.
Yes.
Completely different.
I will agree there too, yes.
Which would be more conducive for the survivability of that dust in this type of event.
Right. The paper did mention that it could be anything from a Neptune-sized object to a Jupiter-sized object.
Yeah, because there's uncertainty on the size, obviously, right?
So
but even if it is dust, you just wonder what part of that. I mean, outside of Jupiter, there's dust, right? In the Jovian system, right?
But if this was a swallowed planet, which it looks like it was, you would also have had it streaming off the atmosphere. The hydrogen, helium, ammonia, and CO and CO2 and all that would have been being blown off as it spiraled into the star. So you would have probably been left with just the core.
Yeah, well, that's what I'm thinking. Is there, like, if you were to probe down into this planet before it got destroyed, and you were to look at the different layers of its atmosphere, would you get to a point where you reach an area where there's essentially,
rock.
Yeah. A rocky layer, rocky surface.
And we still don't know if Jupiter or Saturn
has that. And that would be responsible for the dust that we see.
Absolutely.
Interesting.
Was
there anything else?
Lovely stuff.
Is there any, the outer atmosphere of this planet contributed to changes in the spectrum of the star?
This paper that I saw did not refer to any spectral other than SED and things like that. So I don't know if they spotted contaminants in the
because you think
stellar
like
atmosphere.
helium,
Right.
or I should say methane or something like that, ammonia.
Titanium
Right.
oxide.
Any of this stuff would be dumped into
the atmosphere.
the atmosphere of the star from that planet to the point where it affect the spectrum in some way.
Right.
Of course, you got to factor in the temperature difference and things like that, right? It'd be disassociate a lot of those molecules.
It would definitely be interesting to have seen a before and after spectrum.
Yeah.
Before the flare and then after. And if you saw an enrichment in what we astronomers call metals, yeah.
And the other thing to look at is
a planet.
The other thing to look at is stability. How long will this effect arrive, or would it be to the point where this stuff will just rain down on the star or get destroyed eventually, right? So the signature would wash away.
Okay, we've got somebody. Wanda is asking for the title of paper again. It's here on this slide. It's revealing a main sequence star that consumed a planet with JWST. And it was in the Astrophysical Journal, April 2025, I think it was.
Interesting.
So the news has been out. It's just you're starting to hear it circulated among the normal press.
Yeah, so you definitely take follow-up imaging on a year later.
Yes.
And see what has changed.
And
that would be interesting.
Would imagine that's going to happen.
Yeah, for sure.
So.
Okay, well.
Yep.
That's it for today. So that hour went fast.
That hour went pretty quick, like they usually do.
Now, if you're interested, of course, in learning about these wonderful events that we describe on a weekly basis, one of the things you can do is get involved at higher education level.
Right. And we'd especially like to see you at the University of North Dakota.
Be a lifelong learner.
Yep.
So we have classes both on campus and online, and fill your boots, as they say. And
that's it.
find something that you have a passion for and go with it. Now, our next podcast will be next Tuesday, so that's May the 20th.
Mm-hmm.
We always leave you with a quote at the end of our podcast.
Okay.
So today's quote I decided to make because we talked about them, and it's related to black holes.
Okay.
In fact, do you know the first person that actually thought about the formation of a black hole?
That would almost certainly be Einstein or one of his contemporaries.
Way before that.
Really?
Yeah, it comes from the idea that if you think of light as particles,
okay.
Remember Newton thought light was made up of corpuscles?
Corpuscular light, yeah.
So if you think of light made of particles, and imagine particles being emitted from a body, like a star, those particles would be affected by the gravitational pull of that star.
Right.
So if you increase the mass of that star, and you keep increasing it, there will become a point eventually what would happen.
Well, the little particles of light can't get away from it.
Can't get away. So you essentially formed a
black hole.
A black hole.
So who thought of that? Was it Newton?
No, it was John Mitchell.
Okay.
He wrote a paper and gave it to Cavendish, famous scientist, on November 27th, 1783.
Wow. Wow.
Way like 150 years roughly, before Einstein's general theory of relativity, based on Newtonian universal law of gravity and using the thought experiment we just mentioned.
Cavendish was the first one, if I'm not mistaken, to measure
capital G,
the gravitational constant.
Exactly. So here's the quote from John Mitchell in his paper. Quote, if the semi-diameter of a sphere of the same density as the sun in the proportion of 500 to 1, and by supposing light to be attracted by the same force in proportion to its mass with other bodies, all light emitted from such a body would be made to return inwards it by its own proper gravity.
Nice. That's a black hole, folks.
That's a black hole. Anyways, if you would like to learn more about black holes, we certainly will cover them in the future. That seems to be a favorite topic of ours. We always come back to that. If you liked this podcast as it is, please remember to give us a thumbs up.
2 thumbs up.
That's the movie review. This is a
That's
podcast.
Right.
Only one thumb up.
Okay, one.
Just kidding. And also, if you haven't subscribed, please consider subscribing. Until next time, thank you very much.
Thank you, folks. Y'all have a great day.